Chapter 16 is about polynomial rings. Let me just quickly summarize the main facts of chapter 16. One big theorem is this one. If D is an integral domain, then the ring of polynomials with coefficients from D is also an integral domain, no zero divisors. If D doesn't have any zero divisors, then this ring of polynomials will not have any zero divisors. I hope that makes some intuitive sense. There's a division algorithm. Let F be a field. Okay, so we're not just talking about an integral domain there. We're talking about a field. And F of X and G of X are polynomials in this polynomial ring. This is not a field, even though this is. You're going to see that every day till the test next week. Even though F could be a field, the ring of polynomials is never a field. I'd have to create the ring of the field of rational functions to talk about a field. And the essence of what we're about to do here is think about what happens when you divide by G of X. So we don't want G of X to be zero. When you divide F of X by G of X, you get a quotient Q of X and a remainder R of X. So that this equation is true. This is just like the division algorithm for numbers. Quotient and a remainder. Although with numbers, the remainder was either zero or something less than what we were dividing by. And with polynomials, the remainder is either zero or has a degree less than what we were dividing by. So you get something with a remainder that is a smaller degree of what you're dividing by. In numerical analysis this spring, we had a day where all we talked about was polynomials, and we did some long division and we did some synthetic division. We will do that in here. Probably not today, maybe next Monday. Including long division and synthetic division mod some prime P. That gets really fun. Yeah, most commonly F might be the rationals or the reals, or ZP for some prime P when we're thinking about this. It's got a kind of a long proof, and they do a long division example actually worth studying. But I want to move on to some corollaries, important corollaries. And these corollaries even are called theorems. Corollary 1 is called the remainder theorem. Let F be a field, let A be an element of A, and F of X be a polynomial in the ring of polynomials with coefficients from a field. Then F of A is the remainder in the division of F of X by X minus A. Actually, we can briefly think about proving these things without actually writing the proofs. We're dividing F of X by X minus A. We got to get a quotient Q of X and a remainder R of X that is either zero or has a degree less than what we're dividing by. We're dividing F of X by X minus A, has degree 1. So R has got to be actually a constant polynomial. A number, if you like, a field element. I'm thinking about the division algorithm here when I'm writing this. I'm imagining dividing F of X by X minus A. The division algorithm says I get a quotient and a remainder. The remainder is either the zero polynomial or has a degree less than what I'm dividing by. But what I'm dividing by has degree 1. So whether it's 0 or something else, it's got to be constant. Now just plug in A. And yes, in a field, A minus A is 0, the additive identity. And yes, the additive identity times any field element is 0. That's the essence of the proof of the remainder theorem. F of A is the remainder in the division of F of X by X minus A. R equals F of A. Actually, the remainder theorem is often taught in high school math courses. Did you know that? Maybe you don't remember it. You probably saw this theorem before, but you weren't talking about fields, right? You're just thinking about rational numbers and real numbers without calling them fields. And you're thinking about factoring and that kind of thing, and long division, perhaps, of polynomials. And you already knew this theorem too, that's related, the factor theorem. Ultimately, A is a zero of f of x if and only if x minus a is a factor of f of x. A is a zero of f if f of a equals 0, meaning r is 0 in this long division, in this dividing f of x by x minus a, r is 0, meaning this equation would be true with that thing being 0. X minus a would be a factor. Theorem 16.3, kind of similar to the fundamental theorem of algebra, not exactly the same. In fact, it is different. In fact, it's much easier to prove. The claim is a polynomial of degree n over a field has at most n zeros, counting multiplicity. What does the fundamental theorem of algebra say? Actually, the fundamental theorem of algebra refers to some specific fields. Historically, it said any polynomial with integer coefficients has at least one complex root, where you include real numbers as being complex numbers as well. It actually can be generalized to say any polynomial with even complex coefficients has at least one complex root. Notice the word at least one. That theorem, the fundamental theorem of algebra, is super hard to prove. If you're using a pure algebraic approach, it's really, really super hard to prove. It's possible, but it's very, very difficult. An easier proof uses complex analysis, which is a very fun subject about complex functions and their differentiability and their integrability, taking derivatives and doing integrals. And it's a very, very fun subject. I'd highly recommend studying it at some point in your life, maybe 50 years from now. Very interesting, and you can use some pretty kind of neat theorems in there to prove the fundamental theorem of algebra pretty easily, actually, once you got those theorems. But you got to get to those theorems in the first place, and that it's sort of a weird and winding path to proving the fundamental theorem of algebra. But this is not the fundamental theorem of algebra. This doesn't say it's got at least 1 0. It says it has at most n zeros, no more than n. That's much easier to prove. The proof is that long. You're not going to have more than n zeros, is what this is saying. It's not guaranteeing you have any, but you're not going to have more than n when the degree is n. It's worth studying this example in depth. I'm going to skip it for the moment. The complex zeros of x to the n minus 1. Think about complex numbers a little bit more depth. We did briefly talk about that back in February. Complex roots of unity. These last two theorems I had mentioned before. Based on a definition, a principal ideal domain is an integral domain in which every ideal is a principal ideal. We were talking about this the other day, and we're talking about how ZX actually is not a principal ideal domain. But RX is. If F is a field, then Fx is a principal ideal domain. Yeah, if F equals the real numbers R, then every ideal is a principal ideal, it turns out. If you're feeling confused about trying to remember what we did the other day, I did record it. You could look it up. And finally, this theorem is going to be pretty important for us. Let F be a field, let I be a non-zero ideal. I will be the principal ideal generated by g of x if and only if g of x is a polynomial of minimum degree in I. So ideals in this kind of principal ideal domain are generated by, or can be generated at least by, elements of minimum degree. That sounds kind of ideal. Sounds like that's what you'd want to shoot for, right? We don't like really high degree polynomials. I mean, nobody wants to think about a 1,000,000 degree polynomial. Unless it was like just x to the 1,000,000 power or something. Right? We like degrees 1, 2, 3, maybe 4 or 5 if push comes to shove. We don't really like going much beyond degree 5. So if we can find a minimal degree polynomial to generate our ideal, that sounds good.